In this video, we're going to be talking about injection molding versus urethane casting and 3D printing for manufacture. We're going to look at some actual quote numbers from Fictiv. I'm going to give you my opinion on the subject, so stay tuned. Hey everyone, this is Matt with Learn Everything About Design, and in this video, we're going to do something a little bit different. There's not going to be a how-to or tutorial on design, but instead we're going to look at 3D printing, urethane casting, and injection molding for manufacture. And this has been a topic that's been pretty popular lately. I'm not going to call out any specific channels, but there are some that are pushing FDM for manufacture. And I think it's important that we get another opinion as opposed to somebody who's actually selling an FDM service. So in this video, we're going to look at some quote numbers from Fictiv, but this video is not sponsored by Fictiv. You can use Proto Labs or Xometry or whoever you want to do your own test and quote to make sure that you get the best prices possible. I'm going to be putting all the numbers in the beginning of this video, so if you're only interested in and looking at the raw numbers, we'll talk about that first. And then later on, I'm going to get into my experience, some samples of different types of prints and injection molded parts, and give you my own opinion on the subject. So if you're just here for the numbers, stick around for the first few minutes. If you want to hear more of the background and details and all that information, you can stay to the later parts of the video or check the chapters in the description. So first things first, we're looking at a game controller. Now I'll talk more about the design later on in the video, but I designed this based on a course I'm doing on learneverythingaboutdesign.com, where we go through the PCB design as well as the housing for 3D printing. I redesigned this housing for injection molding with injection molding specific features. So I have a version for 3D printing and a version for injection molding. Neither one is perfectly optimized for either process. And what I mean by that is I didn't give benefit to injection molding over 3D printing, and the same thing for the opposite. I didn't make it perfect for either process because I wanted to keep them as close as possible to give them each the best chance at being consistent in the quotes. So now the quotes. This is probably what you're most interested in. I looked at the different materials available and I tried to keep them consistent, but that's not possible across all the different types of 3D printing. So for FDM, we're looking at an ABS material, and the overall quote to make 50 game controllers, that's 200 of the round buttons, 100 of the oval buttons, and 50 of each piece of the controller, was $8,400. When we look at the SLA, which is going to be a higher quality print, it's going to be a little bit more like an injection molded part, that was $15,000. Now the material was an ABS-like material because there's not an ABS material for this resin process, but the mechanical properties are fairly close. You just end up having a lot of post-processing that has to happen, supports need to be removed, and just in general, the process is more expensive. As we move on to SLS, this was a nylon material. So again, not ABS, but the total quote was around $5,500 for the same number of parts. When you talk about SLS, you talk about generally a little bit of a rougher surface finish. However, this is a self-supporting process, meaning we don't have to worry about supports or overhangs. It just gives us a little bit more design flexibility. The next process I looked at was urethane casting. Now, this is surprising that it came in around $8,400 for the same number of parts. So this is a direct competitor for the price of FDM. Now with urethane casting, we don't have an ABS material. Again, we have ABS-like material, but the end result of a urethane cast part is much closer to an injection molded part than anything an FDM will ever produce. And the last thing I looked at was injection molding. Now, injection molding comes in around $10,000. This can be a little bit misleading because around $9,000 of that is the cost of the mold. So once we get outside of making 50 total controllers, then you're looking at a big difference in price because each controller is only around $20. So this brings me to my next point. If we break this out as FDM versus injection molding, which is one of the more common talking points, that really starts to show how beneficial injection molding is. Now for this, we're only looking at the cost. I'm not talking about the quality or the surface finish or any other aspects of this. We're purely looking at the dollar amounts. So when we look at injection molding versus FDM in an ABS material, again at 50, we're talking about $8,400 versus $10,280, so a little bit over $10,000. Now it's important to note that the FDM cost is going to drop a little bit the more we print, but it is always going to be fixed at a relatively large number. The controllers are about $160 for the plastic parts to make one controller. And for injection molding, that number, of course, it factors in the cost of the mold, but is roughly $20 for just the plastic pieces and then the $9,000 for the mold. So it does cost a bit more initially per unit, but as we see when we get to 250, that number drops considerably. So for FDM, we're at $40,000. For injection molding, we're at $10,990. Now, if you're paying attention, we only went up about $700 or $800 to get an extra 200 units. And that's because when you're talking about injection molding, the mold cost is a big upfront cost, but if you set up a mold to produce 50 units, or if you set it up to produce 10,000 units, the cost per part actually drops a good bit because the setup cost, the time that it takes to actually put these in the machine and get everything set up and running, does factor into the cost per part. So the more that you make, the further that price is going to drop to a certain point. Now, from this point on, I extrapolated the numbers out, so I didn't get quotes at each of these points. But for FDM, I took into account the price drop per unit, and I tried to factor that in a little bit. But with FDM, I kept the per unit cost of $7.50 to build one controller. I kept that the same all the way out to 10,000 units, but in reality, that would drop more. So for 500 units, you're at almost $80,000 for FDM, $12,880 for injection molding. Out to 1,000 units, we're at $156,000 for FDM, $16,500 for injection molding. 5,000 units, you're at about $800,000 for FDM, $45,500 for injection molding. And out to 10,000 units, $1.6 million for FDM and $82,000 for injection molding. Now, when we look at these numbers, that is a pretty big difference to make the same number of parts. Now, could you get a cheaper FDM price through a different supplier than Fictiv? Possibly, but it's still not going to address some of the issues with FDM, and there is no possible way that these FDM parts are ever going to be as cheap as the injection molding parts. Because if you add more parts to a build or add more machines, you're not reducing the amount of time it takes to make the part. When you make more injection molded pieces, you're factoring in the setup cost, so the amount of time it takes to produce the mold first off and the cost for that, but the amount of time it takes to set up and run that process. You have a single mold that's spitting out these parts relatively quickly, and the more parts you make, the cheaper per part cost it's going to be. There's less overall handling of the parts. The setup for the material is done in one specific instance. These are all factors that come into play. But just from the pure numbers, not even looking at quality or the surface finish or any of that stuff, $1.6 million versus $82,000 is quite a big difference. So with the pure numbers out of the way, we have to talk about a couple of other talking points. So what we're going to do now is we're going to talk about the different printing processes. We're going to look at some examples. We're going to talk about where they fit, where they don't fit. And then I'm going to give you some information about my experience, where I come from, what I design, and that sort of thing, so you can understand how my opinion factors into this. So first, FDM. Now, FDM is one of these things that we live with for the sake of convenience. Now, I've got an Ender 7 here. I've got a K1 Max on the way that I just ordered. And these are machines that you can buy for a couple of $100s. The K1 Max on sale was $699 that I bought. And that has a lot of potential in terms of speed, the materials it can print, the accuracy. But it doesn't get rid of two main points. And that is going to be the layer lines. Now, with a part like this is a cell phone amp speaker thing that I made, and I use this every day. It's perfectly fine for a one-off, but if we have curves that go up in the Z direction, the drastic change in curvature there means that we're going to see those stepped layer lines. When you have a much more gradual curve, like this side here, you still see them, but they're not as apparent, not as drastic. Now, of course, you can finish this part, you can do some sanding or vapor polishing, and it would still be perfectly fine. But the point is that this is fine for a one-off, things that we want to produce here at home. Same thing with little desk clips. Now, I make these, again, I did a Intro to 3D Printing course. That's going to be available soon. And these are little clips that you put on your desk, and then you can route your cables underneath so you can have just a little bit cleaner cable routing. These are perfectly fine for you to print 6 of them, 10 of them, just to use at home. But it's not something that we would mass produce. If I did, I would make this for injection molding, and they would just cost next to nothing to produce after the initial cost of the mold, which would probably be somewhere around $2,000, just guessing. The problem that we have with FDM is that curvature in the Z direction is not great. Now we can do curvature in XY. This is a Core XY machine. The bed slingers as well will do decent curvature if it's on a build platform like this and moving in the XY direction. When we bring that out to the Z direction, we're at the mercy of whatever our layer height is. Now most of the time, if you're using a standard 0.4 nozzle and you're dealing with a 0.2 build layer, then you're gonna see that curve. If you have a fillet on something, you're gonna see that curve. And when I did the controller, I printed it at a slight tilt. I didn't print it flat like this because the fillet at the top would just be pretty nasty. And I didn't print it straight up and down, so I printed it a little bit of an angle, and that gave me really good resolution on the sides where you're holding the controller. But at the top, it's still problematic because as the machine is going back and forth, it's basically trying to build that curve, but it only can do it in, let's say, 0.16 or 0.2 layer build if you're using a small nozzle like a 0.4. So these are problems that we have to deal with. But for 1-off, 2-offs, that's perfectly fine. We can live with it. We can do some hand sanding and finishing and not really have to worry about it. When we get into other types of processes, so the next one here is SLS. Now the SLS process is pretty handy. Now, what I mean by that is we don't have to worry about supports. We can get really creative with overlapping geometry and not have to worry about how it's built because this is done in a bed of powder. And the powder supports the build layer each time we move up. We don't have to worry about building a support with an SLA or an FDM process. So one thing that you're gonna find with things like SLS is you're gonna have a little bit more limited material choices. You're gonna basically be dealing with nylon, whether it's glass or carbon filled, to get the strength. But for this was a drone that I designed for Autodesk. This one was intended to be a little bit flexible. And it needed to be able to fly up to ceilings and not get caught on anything, needed to be able to bump into walls, and having that little bit of flex worked out pretty well. Because it's a quadcopter, when all 4 propellers are sort of ramped up, it stabilizes itself, it flexes a little bit, but we wanted the complexity in a single print, and this is over 13 inches across, with all these little intricate details for vents and things and pieces that were able to flex for holding the batteries, for example. We wanted all these little details to be printed in a single unit, or in that case, two pieces. And SLS was the only choice for that. FDM would have snapped or broken at the layer line. So as we printed this, if it was printed in this orientation, we would have all those weak spots in the layer lines. If it was printed like this or like this, then the layer lines are going to be going right through where the propellers are mounted. So as soon as this thing had a hard landing, it would just snap off. Now that's a problem with FDM. SLS and SLA don't really have that same sort of difficulty with the layer line adhesion. So they're great processes. This part initially, when I quoted it, was around $1,200 with one supplier and around $300 with another. So it does pay to search around and make sure that you are getting the best value. Big parts especially, it's difficult because not every facility has the machine to support that. So they have to get creative in how they position it and build it. With FDM, that's problematic because there are structural issues. The next thing I want to talk about is SLA. Now this is by far the most expensive process, but it's going to give you the most detail. This was a car concept I did for a client over 10 years ago. This thing's been sitting on my shelf, and it's been sitting in sunlight at some time, so I can kind of start to see details of the infill that's used here. This was painted, so it did have a polish done afterwards and painted, but inside of the rims I can see vent holes in the rotors that was really added for details for rendering, and I just sent it off not expecting it to even print those. But it printed things like tread in the tires and those little holes and details inside of there, the lug nuts and details like that. And this was painted over, so that covered up some of that detail. An SLA process is the only way you'd be able to do this. You couldn't get that level of detail with SLS, at least anywhere that you would be able to have it this smooth. You couldn't get it with FDM. Even if you're doing a very small nozzle and a very low build height, you have all the issues of supports and these thin features and all the detail inside the wheel, for example. It just wouldn't be feasible or possible. Now, this did originally cost me about $500. Again, that was 10 plus years ago, and that included being painted. I ordered 2 of these. But again, SLA, that was the only way to go, at least at the time. There might be some other options now, but for the most part, SLA is going to give you these high quality parts. The next SLA part, this was actually a controller I did for a client recently. This is something that you can purchase. It is the Yaman Aero Flight Controller. This is an SLA part. This was printed by Motocelino in Atlanta, Georgia. And all of these pieces, there are dozens of them. I mean, there's over 20 unique pieces in this thing. And all of these were done as demo models. So they were taken to conferences, end users, possible clients were, they were put in their hands, they were plugged in, and they were used for flight simulators, and everything was tested. Now this is an SLA, and this is one of the first production injection molds. They are very similar in terms of fit and finish. The injection mold obviously is a little bit better, but you cannot get something at this level out of an FDM. All the curvature, the parting line is non-planar, and all the buttons and things, there are tons of little details and features because it's designed for injection molding. Now, even though that this was it was an injection mold design, we were able to print it exactly as the injection molded geometry, even though that made it a little bit difficult for things like supports and finishing. But again, not something that you could do with FDM. Would we mass manufacture an SLA? Absolutely not, because these units cost somewhere in the $800 to $1,000 range for all of the different parts and the finishing and everything. So it is quite a big investment when you talk about SLA, but if you're trying to get as close as possible to a finished part, then that's kind of the best option that we have. Now, this is not a production injection mold. This was a first run. And what generally happens when you're designing for injection molding, there will be a little bit of mold rework that's sort of factored in. For example, there are sink marks in the outside of this part, and part of that is so we can determine how deep the cores need to go for the screw bosses. Now, those are features that get inserted into a mold. They're not machined in. They're generally added as a part of the cores that get pulled out. So these are things that are easily changed, just the depth or the end angle of those extra pins that are added. Other areas where you maybe have some slight overlap or maybe need to rework the reveal where the parting line is, those are things that you find when you do these first article tests. Now, functionally speaking, everything is fine with the first article test. The fit and finish is great. The details on the back are great. But you do look for little things like that. Make sure that the texturing is going to be right. Do some color testing. And that's all part of the process. So those are some examples. I don't have any examples of urethane casting, even though I have done that in the past. I don't have anything that I can really show you. But urethane cast parts are a great way to get that time between original design and injection molding where you can get samples. So something like this controller, we could urethane cast it instead of SLA. However, in this case, Motocelino is a contractor I use and was helping with some of the design tasks. So having it printed in-house was a big benefit as opposed to paying for urethane casting, which you generally don't do 1 or 2 with urethane cast. You have a larger quantity. So now I think it's important that we talk about some of the bullet points, and at the very end, I'll give you a little bit of information on my experience. So some of the bullet points that we need to talk about are things like life expectancy and the overall quantity and quality. Now, life expectancy, I've used SLS in use before, and obviously the drone, this was an in-use part, and this was done in 2017, I think. I've flown and crashed both of these, and they've been sitting on shelves for a while, but perfectly fine for an end-use application for what that was. That's not really something that we could injection mold. It's got way too many overlapping features. It could be redesigned as an injection molded part. For example, the venting and things on the top could be changed, and some of the other little details could be changed so that this was an injection molded part. But it's such a big piece that it would be extremely expensive. So for building a handful of them, SLS nylon, maybe even glass or carbon filled would be probably a good option. I have done some end-use applications with SLS where they've had to be submersible or survive outside, And in those cases, we knew that the design was too complex for molding, and we also knew the life expectancy. It had to survive a year. So we did things like planned out which prep and paint to use to help make it more UV stable. We built custom gaskets to seal it off, and we just made sure that everything was able to survive because the electronics inside needed to collect data for a year. So SLS was a great option for that. The size of the part, the fact that the FDM isn't truly like a sealed part, it's going to have those layer lines and infill and things like that. Because of those, FDM wasn't even on the table as an option. And I printed, I think, 100 housings out of SLS nylon. So it was a considerable investment, $20,000 or $30,000 for that project, but SLS was the right choice. Now, as we move into talking about injection molding versus FDM. Now, obviously, the quality of an injection molded part is far above that of an FDM part. I don't think that anybody could make the argument that an FDM part matches the quality of an injection molded part. The surface finish of an injection molded part, the texturing, those are things that just an FDM cannot achieve. And that's not even talking about layer lines. I'm just purely talking about the aesthetics of the process. Because it's being essentially stacked on top of each other, I don't ever see a way that you're going to get the surface finish of an injection molded part unless you vapor polish and hand finish and paint. And that really removes some of the options for using FDM as a mass manufacturing option. Now, when we look at life expectancy, if you're printing FDM parts, let's say these desk clips, and you're printing 1,000 of these things on 1,000 different machines, variations in humidity or the way that the materials were stored or bed temperature, extruder temperature, a slight breeze in the room, these can all have some sort of effect on the final print quality, whether it's a layer line adhesion between or maybe the first build layer, or any of those factors can come into play. When you're talking about injection molding, you have a single source. You have the mold, and you have everything is essentially automated. Now, if you do low production molds, then sometimes you've got cores that are manually pulled for side core features and things like that. But for the most part, the rest of the process is automated pretty tightly. Now, that's not to say that an FDM print farm can't be pretty tightly monitored with humidity and those types of things, but it's important to note that when you're talking about printing 1,000 parts on 1,000 different machines, or you're molding 1,000 parts on one machine, there's a little bit more consistency that happens with the injection molded parts. Now, as we looked at with the injection molded prices, the tipping point is pretty low when we talk about the difference between the cost for injection molding and the cost for FDM. So hopefully that helps understand where you can sort of get in if you're making like these controllers. If you're making 50 of them, the price for FDM is pretty close to the price for injection molding. Now, the price for SLS is quite a bit better. So if you were going to print only 50 of them, maybe SLS would be the right option. Maybe urethane casting would be the right option because it's essentially the same price as FDM. So the next thing is flexibility. Now, that bullet point comes up quite a bit when you're talking about FDM specifically, but 3D printing in general. It's like the talking point is essentially you don't have to be locked into a design. You can make design changes. And to me, as a consumer, that's actually a negative for me. And the reason for that is because when we designed this controller, it had already been in the design process for a long time before I even got involved. And the point where I got involved and helped with the design of the housing and the manufacturer side, that process ended up taking, I think it's like 6 or 7 months. And the design part of it was pretty short, relatively speaking. But we have a lot of other factors that go into this. That comes down to fit and finish, tolerances, the assembly process, making sure parts are designed in a way that they can go together easily. And all of those different factors come into play. When you talk about FDM as a design process, you are restricted by things like build orientation for its strength, the actual layers for the quality of the aesthetics, the fact that you can't really do domed features in the Z-axis because the quality of those are going to be quite a bit less than something like an injection molded part. And these are all factors that restrict your design. And when we're talking about injection molding, we do have things like draft angle and consistent wall thickness, but we're not really restricted in terms of geometry. We're more restricted in terms of making sure things are consistent wall thickness, and we can get around that with creative features. And I can't really show you the inside of these controllers, but a lot of things like openings from the bottom and the top to make sure that you have overhangs and ledges and things of that nature. It can all be done with injection molding, just with a little bit of creativity. So when we think about the topic of flexibility, to me, it's not a big deal. Flexibility in an FDM makes me feel more like a beta tester of a product. If I'm buying something knowing that it's constantly changing and evolving because there are design flaws potentially, that to me is not a selling point. That to me feels like I'm being used as a guinea pig. When we talk about this controller design, again, these 3D prints went into the hands of people at flight conferences and different sponsors and things like that that would be reviewing it and using it. Now, they knew that these were 3D printed prototypes, but it was checking things like button location and form and function and making sure that everything worked as expected. Now, the molds at that point were sort of in progress, but that step in the process to validate the button location and the controller location, that had happened over a long period of time to make sure that everything was in the right location. We tested and refined and changed things even at the very last minute as we were starting to quote and get those mold costs. We made slight tweaks and changes to the design. With that said, I don't want a design that's constantly evolving and changing, feeling like I just bought something and the next day I need to rebuy it again because there's a new version that fixes some problems or is a little bit better. I don't think that's a selling point for the consumers. The only reason that that's a selling point is because on the designer side, you have to be less committal to your design. That means that you can sort of spit these things out quicker. So from a consumer standpoint, I think that's a negative. From a designer standpoint, I can understand wanting that flexibility, but having done this, I think that it's important that you do go through the entire process from quality of life and life expectancy of the parts to fit and finish and form and function and all of that stuff. Even initial like QFD, figuring out what types of things are important to your customers and making sure that those are in the design. It's all part of the process. Just because we can spit designs out quickly doesn't necessarily mean that we should. So it also brings me to my last point, which ties into flexibility. When we look at the controller specifically, there are plenty of other factors that come into play besides just the pure controller itself. As I mentioned, assembly. So if you're producing thousands of something, then there are teams of people that are going to put those things together, test them, assemble them, and package and ship them out. It's not as simple as printing this and knocking it into a box and sending it out. With a controller, for example, the packaging is custom. There's a picture of the controller on every side, and when you open it up, there is custom foam that's cut to hold the controller. There's a space for a USB-C cable that comes with it, and little finger hole so that you can pull the controller out. So these are all different aspects of the design process. Now, it doesn't necessarily just deal with the 3D model, but this goes back to, as a consumer, would you rather see a box that comes in and it's got all of the nice features, a spot for a cable and nice foam to hold your controller to make sure that it survives the journey, or something like this that's just in a random box? Now, to me as a consumer, I would rather spend my money on something that looks a bit more finished and polished, and I know that it's been through that process. So these are just kind of my opinions, obviously, and now I'll talk a little bit about my experience so you can better understand where I'm coming from. At this point, I have been using CAD since the 90s, which is over 30 years at this point. And for a long time, I worked in research and development. Now, working in R&D means that you generally are less concerned about the cost. You're more concerned about the optimal process. So with that, I've done a lot of CAM and CNC. I've done a lot of hand fabrication, welding, sheet metal, composites, as well as 3D printing and injection molding and urethane casting. I basically had a bit of free reign. I had a problem to solve, and then I could explore what was going to be the best option. Knowing that I had to produce one of something or 100 or 1,000 of something, I could explore the options, think about things like 3D printing and issues with UV and how those things affect our parts, making sure that we get UV stable plastics for injection molding versus trying to do an initial test with an SLA part or a machined part. These are all things that come into play as a designer, and the R&D world, the cost is less of an issue, so you can kind of figure out how all these different pieces of the puzzle work. And what I saw in that role is that for a handful of things, sheet metal fabrication, CNC machining, and composites were really the right choice. In a lot of cases, 3D printing at certain volumes was the right choice. And in a lot of cases, injection molding or urethane casting was the right choice. So it's really problem dependent. There's no one size fits all solution. You have to understand the limitations of each of these and figure out which is the best for your solution. Now, when I left that role, I moved into a consulting role where I was doing design consulting and training for all kinds of different companies. Everything from inventors that had product ideas that were looking to prototype and get and sell their idea, to companies like Yaman who were looking for help taking their initial concept and doing a more finalized housing design and working out some details for things like mechanisms and getting it ready for injection molding. I've also helped companies in rail and oil and gas and concept vehicles. So all kinds of different areas where I've worked in design and manufacture, including CAM programming, CNC, and training users in those roles as well. So with all of that, I have a bit of experience in all sort of aspects. I don't claim to be an expert in FDM or all the 3D printing processes, but I've used them all enough to know where they fit into my sort of role. And as a designer, I never go to a customer and lock them into, say, FDM. I always look at the process. I say, what are you making? How many do you want to produce? What's your end goal? And in most cases, that's injection molding. There are very few cases where a 3D print is going to be an end use application other than things that I make here at home. With all that said, that's my experience, my opinion, and this overall example of the process. If you have any questions on that or any feedback or your own comments, please let me know in the comments below. If you want to see more content like this, so not really a how-to, but more talking about some sort of design process or design topic, let me know. I can do more of these videos, but they are a little bit more involved, so if nobody's going to watch them, I don't really want to do them. So if you have any questions or comments, leave them below. As always, thanks for watching. We'll see you in the next one.